So hello everyone, my name is Wang. I'm from Guangdong Technion, assistant professor in chemical engineering department. Today my topic is Ultrasoft on skin electronics for biomedical applications. So in this slide, we can see there are a lot of current commercial wearables, such as the Sony Watch, Google Glass, Fitbit, but they are all based on rigid circuit boards, which they are not flexible or stretchable and cannot conform to the human skin, let alone the stable dynamic contact with the human body. So how will the future electronics will be look like? So this slide shows the ideal second skin wearables, which can take health care to the next level. So on the human skin, we can have the skin sensors to acquire various biosignals, and these biosignals can be processed and sent to the hospitals where the doctors can use for individual health management. And on the human body, we can have the wearable energy devices to support these closed loop systems. So this slide shows the development of wearable electronics, the evolution process. So in 1978, we have the first prosthetic hand, and 10 decades later, we have the first touchable screen computer. In 2004, we have transistor array-based flexible active matrix e-skin, and then researchers use structural engineering to make pressure sensors. And in 2009, we have stretchable OLED. And as time went on, we can see the stretchable electronics are becoming thinner and softer and with more functionalities, such as intelligence, self-powered, self-healing, and visualization, and even with transparency. So in 2011, Professor John Rogers developed epidermal electronics, which exhibit high conformity to the human skin, so they can acquire the health signals with high fidelity. So in this slide, we can show the skin bioelectronics can measure a wide range of biosignals, including physiological signals, ECG, EMG, and biochemical signals, such as molecular ions in sweat or tear or blood, and also the biophysical signals such as skin modulus, strain, pressure, tactile. And the challenges in soft electronics will be presented in this slide. So there are basically two components, which is the soft mechanical segment, which made from the soft polymer materials, and the electrical component is made from the active electrical materials, which is from metal or carbon-based materials. And these two materials have very large mechanical mismatch. So that's where need to delamination or fracture when the device is stretched. So in order to avoid the mechanical mismatch, my strategy is to develop novel materials and use integrated with structural engineering to make devices that can be stretched. So I did my PhD in Monash University and postdoc in the University of Tokyo. So basically, this is what I have been working on to make novel materials and structural engineering and fabricate soft electronics for biomedical applications. So today I will focus on these two works. One work is the standing gold nanowire films, and the other work is the robust self-adhesive nanofilm. The first work is a vertically aligned gold nanowires. So this gold nanowire film can be put in different configurations. So this is an example of the multi-layer structure. And the unique of this film is on the top, there is densely packed nanoparticles, and underlying the nanoparticles, there's vertically aligned gold nanowires. And the nanoparticle size is around 12 nanometers, and diameter of the nanowire will be around 10 nanometers. And this is the optical image of this gold nanowire film. And this the film is fabricated by whole solution processed. And the length of the nanofilm can be tuned, ranging from few hundred nanometers to 14 micrometers. So when directly grow the film on silicon rubber, the film can be stretched to 800% strain without failure. So why this film can be stretched so much? This slide give us an explanation. Because the unique Janus structures, the top layer of the film will be more rigid than the underlying layer. So when the stretch begins, the nanoparticles will start to separate. And when we continue to stretch, the nanowire begin to separate, but the bottom layer of the nanowire will be connected. And this is all due to, this is also due to the glue function of this molecular glue. So they provide the good adhesion between the nanowire and the soft substrate. So this video shows the nanowire array stretching procedures. So we can see the nanoparticle start to separate initially, and then the nanowire start to separate, and the V shape got larger and larger during the process. And when we release the stretching, the V-shaped crack will start to self-adhere to its original state. And as an example, to be used as skin electronics, we use this, we grow this nanowire film on silicon rubber, and we put it on the human skin. Integrated with wireless technologies, we can monitor human emotions in real time. So this is a video for detail. So we put the skin patches on the human skin. The placement of the skin patches is determined by the particular muscles, because each emotions will have particular muscle groups. So in real time, the emotions can be discerned from the remote monitoring. So this is a wireless interface. Then we can in real time differentiate the emotions of this subject. So the second work I want to introduce is a robust nanofilm for long-term health monitoring. It is recently published paper. So the film have an ultra thickness, which is 95 nanometers. And even though it is very thin, the film exhibits excellent elasticity. And this figure shows the film supporting large amount of water without failure. And this is a video showing the supporting process. So why this film exhibits such high robustness? So from the fabrication process, we can see the film is reinforced by nanofibers. So we first, in the beginning, we first electrospun nanofiber mat. With a PI frame to support, and then we deep coating the mat into diluted silicon rubber solution. And after drying and curing, we have the nanofiber reinforced PDMS nanofilm. So with the reinforcement, we can see the mechanical properties of the nanofilm is greatly improved compared to pure PDMS film. And due to the thinness and the softness of the film, the nanofilm can self-adhere to the human skin. Repeatedly, we can see that the film is quite robust. And to evaluate To evaluate the adhesion performance, we use the tag separation test, which we can evaluate the error adhesion energy of this film. And from the results, we can see that the nanofilm exhibit 21 times larger adhesion performance, adhesion energy than the pure PDMS film, and it can also survive over 1,000 adhesion cycles. I mean, attachment and detachment process. And due to its self-adhesiveness, stretchability, and mechanical robustness, we see it's very promising to be used as the subject for skin bioelectronics. So after depositing a layer of gold on the nanofilm, we can have a self-adhesive skin electrode. So this slide shows the actual conformability of the film, and this is a enlarged picture which shows very clear skin morphologies. And this slide shows the electrode can be stretched to over 30%. So that is enough for the ECG monitoring. And the repeatability test shows the electrode is mechanically durable. And then we use this electrode to be used in real life applications. For the long-term ECG monitoring, we attach this film on the human body for 1 week, and during this time, the subject did normal daily life activities such as walking, eating, and shopping, and taking showers. And from the result, we can see the ECG monitoring is quite the electrode maintained quite stable functionalities, and we have 1 week stable ECG results with high accuracy during the whole process. So in conclusions, we can see that the skin electronics evolved from ultra-thin film type electronics to breathable nanomesh type electronics, and then to the breathable adhesive robust nanofilm type skin electronics. So in the end, I want to thank Guangdong Technion and Technion, and also the Monash University and my previous supervisors. And thank you all for listening. Now I welcome questions. Also, I want to mention that I am hiring graduate students and postdocs in my life. Thank you very much.